If you follow any piping system in your plant, you'll come across a lot of different components. Some, like this strainer, you're pretty familiar with. You're often called on to clean or replace strainers and filters. But other components, like pipe hangers, you may not be so familiar with. You see them often enough, but you probably don't know how they work. Pipe hangers are so reliable that they may go for years before they require any attention. But if they do break, your lack of experience in working on them could put you at a real disadvantage in trying to fix them. So in this unit, we'll be discussing a number of common piping components, or piping auxiliaries as they're often called. For each one, we'll explain what its job is, how it accomplishes that job, and we'll point out some routine maintenance that should be performed. Now we'll start with filters and strainers, piping auxiliaries that require quite a bit of maintenance. Then we'll move on to components that don't require as much maintenance, pipe hangers, expansion joints, and surge dampeners. Now this pipe carries water. Over a period of time, the water will cause corrosion on the inside surface of the pipe. This corrosion can cause a lot of problems. To see why, let's look inside the pipe. As the inside wall corrodes, some corrosion products break loose and are carried along by the fluid inside the pipe. If these particles lodge in some critical area, like this valve seat, the valve will not be able to close fully, and some fluid will leak by. Some sort of component is necessary to trap these corrosion products and any other particles in piping systems. There are two similar components that accomplish this job, filters and strainers. Filters typically use a cloth or heavy paper screen to trap contaminants, while strainers usually have a metallic screen. Another difference between filters and strainers is that filter elements are usually layered, while strainers generally have just one surface for fluid to pass through. Here's a representation of a typical strainer screen. You can see that it has just one layer with uniform openings in it. This is known as a surface medium. As fluid passes through a surface medium, particles too large to fit through the openings are trapped in the screen. A typical filter element, on the other hand, has several layers with progressively smaller openings in each one. This is known as a depth medium. As fluid passes through a depth medium, particles are trapped in each layer. In most cases, filter elements can remove smaller particles than strainers can. Now, these distinctions between filters and strainers are good in general, but there are exceptions. Some strainers, for example, do have depth mediums and can remove smaller particles than many filters. And you'll find some filters that do have metallic filter elements. Some filters may even use sand as a filtering medium. So, as we go along, keep in mind that the terms filter and strainer are not clear-cut categories. They're used almost interchangeably. Now, this is a typical Y-type strainer. It's commonly found in steam systems. In this cutaway, you can see the strainer element here. Steam enters through the inlet here. It passes through the strainer and is discharged here. But the strainer has another outlet here. It allows the strainer to be blown down and cleaned of any particles that have collected inside. Here you can see a Y-type strainer installed in a steam line. The blowdown line is here. There's also a blowdown valve. Opening the valve cleans out the strainer. Now here's a filter you're probably familiar with. It's an oil filter from a car engine. In this cutaway, you can see the filter element here. Oil enters through these small holes. It flows across the top of the filter element and then through the heavy paper filter. Finally, the filtered oil leaves through this large hole in the center. Let's look at a typical system where this oil filter might be installed. And keep in mind that what we say about this filter also applies to strainers. Okay, here's the oil reservoir. A pump moves the oil from the reservoir to the equipment being lubricated. The oil returns to the sump through this line. The filter, or strainer, is here. On one side is an inlet line, and on the other side is the outlet line. Finally, there's a gauge to measure the pressure drop across the filter. Now, this is known as a full flow filter arrangement. All the oil that's pumped from the reservoir passes through the filter. But a system like this requires some way to ensure that oil will continue to reach the equipment, even if the filter gets clogged. Otherwise, the equipment could burn up. To make sure that oil continues to flow, there may be a relief line around a full flow filter. If the filter becomes clogged, the relief valve will open, allowing the oil to go around rather than through the filter. In some cases, full flow filters have a built-in relief valve. In this filter, it's nothing more than a small disc held down by a spring. If the filter becomes clogged, pressure will build up inside the casing, causing the spring-loaded valve to lift, discharging the oil directly to the filter outlet. Another filter arrangement is the bypass filter system, or partial flow system, as it is sometimes called. It's designed so that only part of the flow goes through the filter. The rest of the flow goes through the bypass line. This bypass line usually has an orifice to balance flow between the bypass line and the filter. The drawback to this arrangement is that since not all the oil goes through the filter, fewer contaminants will be filtered out. Okay. Now we have one way in which we can classify filters. They can be either full flow or bypass flow. Strainers can also be full flow or bypass flow, but in most cases they are full flow. All right, now, so far we've only discussed a single filter or strainer. Now these are called simplex filters or simplex strainers. If a simplex filter has to be replaced, the system it is in must be shut down. Otherwise, when the filter is removed, fluid will spray all over. Duplex filters, however, are designed to allow filter replacement while the system remains in operation. There are actually two filters side by side. Flow can be directed through one filter or the other. This way, one filter will always be in service, while the other can be isolated for cleaning or replacement. But how do you know when filter maintenance is necessary? Well, in a car, you usually replace the filter every so many miles or so many months. Now, this method works okay most of the time, but it does have problems. If there happens to be a lot of dirt or other contaminants in your oil system, the filter could get clogged long before you get around to changing it. What we need is some positive indication that the filter is doing what it's supposed to do. Now, one way this is done in the plant is to measure the pressure drop in the fluid as it goes through a filter or strainer. When a filter element is new, fluid passes through it easily. The pressure at the filter inlet and outlet are almost the same. But as the filter traps more and more particles, not as much fluid can pass through it. The pressure at the filter inlet increases while the outlet pressure drops. The difference between the filter inlet and outlet pressure is called the differential pressure, or dP. Sometimes dP is also called delta P. In any case, it can be read by comparing the filter inlet and outlet pressures. The difference between them is the dP. Sometimes a dP gauge is installed. In this case, differential pressure can be read directly from the gauge. In our simple oil system, a dP gauge is located here. There's a tap upstream of the filter and one downstream of the filter. When a filter is first installed, there will generally be a small differential pressure because the filter element itself does not create much resistance to flow. But as the filter traps more and more particles, the fluid has a harder time passing through the filter element. The dP rises. When the DP reading reaches a particular value specified by the manufacturer, this is a signal that the filter is clogged and should be replaced. One note of caution. Now, when replacing filter elements, always check that you are using the correct filter replacement. The wrong element might react with the fluid, causing the element to fall apart. Checking the DP takes the guesswork out of knowing when to replace a filter. While the filter is in service, the rise in the DP reading tells you that the filter is doing its job. And at a predetermined amount of DP, you know that the filter is becoming too clogged. Now, if the DP reading did not rise while the filter was in service, you might suspect that there was a hole in the filter and that no contaminants were being filtered out. Okay. So far, we've discussed two ways to classify filters and strainers. We said that filters and strainers can be either full flow or bypass flow. And remember, another name for bypass flow is partial flow. And filters or strainers may be either simplex or duplex. Finally, we saw how to use a DP gauge to determine when a filter or strainer needs replacement. Now, when we come back, we'll show you how to remove, clean, and replace the basket of a full flow duplex strainer. But first, turn off the tape and review the material that we've covered so far. In the last segment, we discussed filters and strainers. We saw how they removed solid particles from fluids using surface or depth mediums. And we gave you some general differences between filters and strainers. We also introduced the concept of differential pressure, or DP. And we explained how a DP gauge, or two pressure gauges, can be used to tell us when a filter or strainer needs to be replaced or cleaned. Now, in this segment, we'll see how to clean a duplex strainer. We'll see another way to read DP, and finally, we'll discuss the unit of measurement for particle size. Now, this is a drawing of a typical lever-type strainer. The inlet is here, and the outlet is in a little lower position on the other side. Here's a cross-section view of the same strainer. The plug valve, located here, directs flow to and from the baskets, here and here. With the plug valve in this position, fluid flows through this basket. This basket is on standby. When it's time to clean the strainer, the first step is to shift strainer baskets. First, rotate this lever. It lifts the plug valve off its seat. Then rotate this lever to move the plug valve. The plug valve now directs flow to this basket, while the other basket is put on standby. To reseat the plug valve, move the first lever back to its original position. Then, open the drain and vent the strainer that has been isolated. Once the strainer has been vented, it can be opened and the basket removed for cleaning. Now, here's another duplex strainer. It's installed in a pump suction line. It has hand wheels instead of levers, and it has no drain valve. The DP across this strainer can be read from a single vacuum gauge that has two pointers. It's a vacuum gauge because the line where the strainer is located is operating under a negative pressure. The top pointer indicates the strainer outlet pressure, and the bottom pointer indicates the strainer inlet pressure. When DP increases, the pointers spread further apart. The difference between the two pointers is the actual DP. Let's look at this drawing of the strainer to see how it works. The inlet to the strainer is here, and the outlet here. Flow passes through this strainer while the other strainer is isolated. Rotating this hand wheel causes this inlet valve to close and this one to open. Rotating the other hand wheel causes this outlet valve to close and this one to open. After both hand wheels have been rotated, the strainers are reversed. Now, this strainer is in service. Okay, now that we're familiar with how the strainer works, let's watch a mechanic shift and clean a strainer basket. He shifts the strainers by turning the hand wheels. If the hand wheels are hard to turn, as these are, first rotate one and then the other until they've both been rotated as far as they'll go. If the hand wheels are easy to turn, they should both be turned together. Once the strainers have been shifted, the next step is to vent the strainer that's going to be cleaned. But first, one of the strong backs holding the strainer cover in place is removed. Now this makes it a lot easier to reach the vent valve. Once the strong back is lifted out of the way, the vent can be opened, allowing the vacuum inside the strainer to be broken. Then the second strong back can be removed and the strainer cover lifted. Now the basket can be removed and inspected. This one has some debris in it that must be cleaned out. If there is a cleaning station available, use it to clean the basket. You can then replace the basket, close the vent cover, and secure the strong backs. Now, crack the hand wheels enough to direct some flow through the strainer that's just been cleaned. This will get rid of any trapped air. Keep your eye on the pump suction pressure. It should remain steady. Then return the hand wheels to their original position. Duplex strainers like this are pretty durable, and most of the time the only maintenance you'll have to perform is to clean out the baskets. But occasionally the valve that separates the two sides will wear, causing fluid to leak by the seat. Now if this happens, you'll probably have to lap the valve seat. You may even have to replace the whole valve. Also, you may find gasket leaks, but a new gasket will quickly remedy that problem. Y-type strainers are also pretty dependable, but contaminants can get packed down, clogging the strainer. Now, if this happens and blowing down the strainer doesn't help, the only thing to do is to take the strainer apart and clean it. Sometimes installing the strainer upside down will keep it from clogging. So will frequent blowdown. The process for changing out filters is basically the same as that for strainers, with one important difference. With filters, the filter element itself is usually replaced with a new element rather than cleaned and reinstalled, like strainer baskets. And remember, if you're installing a new filter in an oil system, rub a thin layer of fresh, clean oil on the gasket. This will ensure a better seal and will reduce the chances of tearing the gasket. Filter elements made of cloth or paper are thrown away because they're generally less expensive than wire strainer baskets. And because filters can trap much smaller particles than strainers, they would be a lot harder to clean. You see, some of the particles that we have to deal with are so small that they can't be seen without a magnifying glass or a microscope. The unit of measurement that is used to describe these particles is called a micron. A single grain of salt, which you might think is pretty small, is actually about 100 microns. And compared to the size of the particles that some filters can remove, a grain of salt is enormous. Now, filters can remove particles that are only a fraction of a micron. Strainers can typically remove particles no smaller than 5 microns. Strainers, or filter elements, all have ratings that'll tell you the size of the smallest particle they can remove. If, for example, you need a filter for a fuel nozzle that has an opening of 16/1000ths of an inch, or 0.4 millimeters, the filter you put in must be able to remove particles that are smaller than the opening in the nozzle. As a general rule, if there's a critical opening or orifice that you must protect, like a fuel nozzle, the filter you use should be able to remove particles 1/2 the size of the opening. So, in our example with the fuel nozzle, to protect a 16,000th inch orifice, you need a filter that can remove particles that are only 8/1000ths of an inch. Now, this is roughly equivalent to 200 microns. Now, if you need to ensure a liquid is clear, you'll need a filter with a 25 micron or finer rating. And to remove a haze from a liquid, a 10 micron rating would probably be needed. You know, most of the time you can tell there's a strainer or a filter in a pipe simply by looking at the pipe, but sometimes you can't. This pipe, for example, has a cone strainer in it. From the outside, the only indication is this short spool connection. But in this drawing, you can see the cone-shaped strainer inside the pipe. And there's usually a spool piece in front of the cone itself. If the cone becomes clogged, the spool piece is removed first. Then the cone is taken out and cleaned. Next, we'll look at 3 special application filters in a little more detail than we've covered up till now. But before we do, I think this is a good place to stop and review the material that we've already covered. In the last 2 segments, we made some general distinctions between filters and strainers. Filters, we said, usually have disposable paper or cloth depth mediums. Strainer screens are usually metallic surface mediums which can be cleaned and reused. Now, you may remember that we also said there are exceptions to this rule. And in this segment, we'll see some of those exceptions as we discuss 3 special application filters. Knife edge filters, backwash filters, and pre-coat filters. Now, this is a typical knife edge filter. One of its characteristic features is this handle. Shortly we'll see what its purpose is. Inside the filter is a series of metal plates or discs separated by spacers. There may be several hundred of these plates. The stack of plates and spacers is connected through the center to the handle. In this exploded view, you can see 2 filter discs and a spacer. There are also fixed cleaner blades here between the discs. The distance between the discs determines the size of the particle that the filter can trap. Knife edge filters normally filter down to about 40 microns in size. Fluid enters through an opening in the casing, flows into the gap between the filter plates, and continues upward through the center of the discs. Any particles too large to fit between the filter plates will be trapped on the outside of the plates. Then when the handle is turned, the discs move past the fixed cleaning blades. Particles that have collected on the discs are dislodged and dropped to the bottom of the casing. The bottom of the casing must be cleaned occasionally and all dirt deposits removed. One of the obvious advantages of knife edge filters is that they can be cleaned while the system is in operation, while fluid is flowing through them. Now, this makes them ideal for systems which are in constant operation and should not be shut down. They're often found in low flow, medium to low temperature systems, and they may filter oil, air, or water. Backwash filters are another type of special filter. While there are many different backwash filter designs, they all work on the same principle. Flow through the filter element can be reversed, causing the trapped particles to be dislodged and flushed from the filter. Such filters are frequently found in water treatment systems. This drawing is of a backwash filter with just 2 metal filter elements, but most backwash filters will have more than 2 elements. Some may have as many as 20 or more elements. And the filters are typically quite large, up to 10 or 15 feet in diameter. During the filtering process, water enters here, it flows into the hollow core of the filter elements, and passes through the wire windings that make up the filter screen. Particles too large to pass through the windings are trapped on the inside surface of the screen. The filtered water is then discharged here. Now, In most cases, there will be a separate inlet and outlet for backwashing. When the dP across the filter reaches a certain predetermined value, the inlet and outlet ports for the filtering process are closed. The backwash lines are opened and the water is sent backwards through the filter. This backwash flow dislodges and flushes out particles that are trapped on the inside of the filter screen. A backwash filter with just a few elements like this one would require the system to be shut down for backwashing. If the backwash filter has quite a few elements, though, it may be designed so that one element at a time can be backwashed while the filter remains in operation. And the same is true of a second type of backwash filter that uses sand or similar material as a filtering medium. Normal flow is in this direction. As particles become trapped in the sand, the dP increases. The filter is then cleaned by reversing the flow and flushing out the contaminants. And there are screens located here and here that keep the sand itself from being flushed out of the filter. These screens should be inspected for holes periodically. In these filters, the backwash mechanism is often quite complex and may be automatically operated by electric, pneumatic, or hydraulic operators. This is covered in more detail in your text. The important thing to remember here is that there are a number of filters that are cleaned by reversing the direction of flow through the filter. A third filter that's similar to a backwash filter is the pre-coat filter. A pre-coat filter has two different filter mediums. First, there is a cartridge that's usually made of metal and is similar to backwash filter elements we've discussed. What's different is that this filter element is coated with a second filtering medium called a pre-coat. Pre-coat material is usually a powdery wood product, but it can be a synthetic product. Pre-coat material, in combination with the filter element, enables these filters to remove very small particles. Normal flow through a pre-coat filter is opposite to the flow in the backwash filter we saw. Fluid enters here, passes through the pre-coat material and the filter cartridge, and is then discharged here. Contaminants are trapped in both filter mediums. When the pre-coat filter requires cleaning, the inlet and outlet are closed off, and a backwash is directed through the filter like this. The backwash dislodges the trapped particles as well as the pre-coat material itself. It's all discharged out the backwash drain. To get new pre-coat material into the filter, there's a separate pre-coat inlet here and an outlet here. The pre-coat is mixed with water and fed into the filter. The pre-coat is deposited on the filter elements, while the water it was mixed with is drained off here. A sight glass may be provided to check the coating on the filter element and make sure it has attached properly. If it has, the filter can be returned to service. But sometimes, after extended service, so many contaminants collect on the filters that they can't be cleaned through backwashing. Some of these contaminants may be oily and will prevent the pre-coat from attaching to the filter elements. If this happens, the elements may have to be removed and steam cleaned. Similarly, with backwash filters, if elements remain clogged even after repeated backwashing, they'll have to be cleaned or replaced. And if sand were being used as a filtering medium, the sand would have to be replaced if backwashing failed to clean it. If the plates in a knife-edge filter became clogged, you may find yourself unable to turn the handle. Now, if this happens, don't force the handle, or you'll probably damage the discs inside. Instead, take the filter apart and soak it in a solvent recommended by the filter manufacturer. If the discs are really clogged, it may be easier to simply replace the entire disc assembly. Now, one good way to keep the discs from getting really clogged is to periodically remove the drain plug and clean out any dirt and sludge that has collected in the bottom of the filter. Well, so far, we've looked at quite a few strainers and filters, and we've seen that they use many methods to accomplish the same job, the job of removing contaminants from fluids. Now, when something goes wrong with a strainer or a filter in your plant, you should be able to identify what type of strainer or filter it is and know basically how it works. Believe me, this knowledge will help you to fix the equipment quickly and easily. Now, when we come back, we're going to look at a piping component that you may not have worked on very often, but one that's more common in the plant than either strainers or filters. But first, turn off the tape and review the material in your text. Replacing or cleaning filters and strainers is, or will be, a pretty common experience for you as a mechanic. But how often have you done work or seen work being performed on pipe hangers? Probably not very often. Pipe hangers may last for years and require little attention. They just sit there doing their job. The problem with really reliable parts is that when they do break, you may be unfamiliar with how they're supposed to work, and this puts you at a disadvantage in trying to repair them. In the rest of this unit, we'll try to take care of that problem by discussing some of the more reliable piping auxiliaries in the plant. Let's start by looking at how pipes are held in place. Pipe supports are used to secure piping from underneath the pipe. Pipe hangers hold pipes from above. Whenever piping is installed, it's essential that some way be found to keep it in its proper position. Hangers and other pipe supports not only keep a piping system in place, they also provide for controlled movement of pipes. You see, pipes rarely stay in one place, and there are several things that cause pipes to move. As piping systems heat up and cool down, the pipes themselves expand and contract. Vibration of plant machinery also causes the pipes to vibrate. And when valves are opened or closed, the rapid change in flow can cause pipes to move. Now, if all pipes could be run along the floor, there wouldn't be much need for support structures. But then there wouldn't be much room for anything else either. Also, many pipes in the plant go through floors and walls, and without adequate support, they'd quickly weaken and break. Well, let's see what devices are used to keep pipes in place. A simple pipe support consists of a clamp that can be attached directly to a pipe and to a permanent fixture, such as a wall. Or a pipe might be supported by another smaller pipe which is welded in place. But neither of these pipe supports allows for any pipe movement. Now, in small pipes or pipes that don't heat up and cool down, movement may not be a problem, but in larger pipes and ones that do have temperature fluctuations, normal movement must be allowed for. A pipe saddle is one approach. The pipe rests in the saddle and can slide back and forth. But if a lot of movement takes place, wear will occur where the pipe and pipe saddle meet. A pipe roll solves this problem. It both supports the pipe and allows it to move back and forth without friction. The frame of the pipe roll is attached to a permanent fixture. The pipe rests on the roller. As the pipe moves, the roller moves with it. These support components we've mentioned, the clamp, saddle, and roller, all support pipes from the bottom. Hangers, on the other hand, support pipes from the top. Now, here's an example of a typical pipe hanger. It has three basic parts. First is the upper component. It attaches to a permanent fixture, such as an I-beam. Next is the intermediate component. It connects the upper and lower parts of the pipe hanger. Finally, here is the lower component, which attaches directly to the pipe itself. Some common upper components include this beam clamp and this welded beam attachment. Intermediate components are usually either rods or a combination of rods and turnbuckles. And lower components, even though their design may vary, are simply some type of ring that attaches to the pipe itself. Okay, now that we've seen the simplest examples of pipe hangers, let's look at two more examples that are a little more complicated. Here's a spring hanger. The intermediate component is a rod and spring mechanism that improves the ability of the pipe hanger to absorb shock. Spring hangers may use one or more springs to regulate pipe movement. A refinement of the spring hanger is the constant support hanger. Constant support hangers are designed to balance the load and spring tension regardless of the pipe angle. In this constant support hanger, there are two dots that indicate the proper adjustment for both hot and cold conditions. If the hanger requires adjustment, it's accomplished by moving this nut. Part of your job will be to check pipe hangers to see that they are keeping the pipes in place and are giving adequate support for the piping system. Parts may vibrate loose and require retightening or replacement. And leaking joints and bent or sagging pipes can be indications of improper pipe support. Pipes and their support should be checked on a regular basis. However, if at any time you see sagging pipes or obvious signs of wear on the pipe or hanger, don't hesitate to inspect the pipe then and there. You want to be sure to check whether or not a leak or sag is really caused by improper support. There could be other causes for this problem, such as someone abusing the pipe by standing on it. Pipes are not meant to be used as step ladders or chairs. Also, between the support or hanger and the pipe itself, you may find canvas or rubber protective material. Now, this should also be checked routinely. If the protective material is worn out, the movement of the metal pipe against the metal hanger or support can weaken the piping at the point of contact. Okay. Next, we're going to look at two special application pipe hangers to see how pipes can be protected from severe shock. But first, stop the tape and review your text material. In the last segment, we saw a number of mechanisms that support pipes while still allowing normal pipe movement. Now, in this segment, we'll see two special types of pipe hangers that protect against severe shock, like water hammer or even an earthquake. Now, these two special devices are called shock arrestors or snubbers, and we'll look at both a hydraulic and a mechanical snubber. As its name implies, a hydraulic snubber uses a fluid to absorb shocks, while a mechanical snubber uses mechanical components like springs and inertia masses to dampen shocks. Let's begin by looking at a hydraulic snubber. Now, this diagram will show you its basic principle of operation. Here, of course, is the casing. It's filled with hydraulic fluid supplied by this reservoir. One end of the casing is attached to a permanent support structure, such as an I-beam. The other end of the casing is penetrated by a piston rod that's connected to the piping we want to protect. Any movement of the pipe also causes the piston to move, and as the piston moves, it displaces hydraulic fluid. If the piping movement is slow, say when the pipe is heating up, then the piston will also move slowly, and the hydraulic fluid will be able to move freely through this orifice. This orifice is surrounded by two check valves. This check valve responds to fluid movement in this direction. Likewise, this valve responds to fluid moving in this direction. A third check valve here prevents backflow of hydraulic fluid from the cylinder back into the reservoir. Okay, so when the pipe is expanding, the piston pushes fluid slowly enough to go through the orifice without closing the check valve. The controlled movement of the pipe is unrestricted. But if there's a sudden shock to the pipe, its increased movement will be transmitted to the piston. The hydraulic fluid will be pushed with such force that it'll close the check valve. And when the check valve closes, fluid is redirected through this smaller orifice. But not as much fluid can get through this smaller opening. The restriction to the flow forces the piston to slow down. And since the piston is directly connected to the pipe, the uncontrolled movement of the pipe is also restricted. The pipe is protected against serious damage from excessive movement. Now, mechanical snubbers do the same basic job as hydraulic snubbers, but they do it in a different way, a more complicated one. So a little more detail is necessary to explain how they work. We'll be using this cross-sectional view, as well as an exploded view of some of the parts to get a better idea of how it works. Here, you can see the main parts. The casing is here. This end of it is attached to a permanent support. There's a telescoping cylinder here. One end of it attaches to the pipe we're protecting. The other end is threaded and meshes with this threaded shaft. The threaded shaft extends into the casing and forms a cylinder called the torque transfer drum. Now already, we can see that equipment movement will be transmitted to the telescoping cylinder here. When the telescoping cylinder moves in or out, it will cause the shaft and the torque transfer drum to rotate. Now let's finish identifying the parts before we talk any more about how the snubber works. Inside the torque transfer drum is a spring. Part of the spring extends through an opening in the drum, where it engages with a part called the inertia mass. The inertia mass weighs more than any of the other parts that we've mentioned. Ball bearings here maintain the correct relationship between the parts. Okay? Now let's look at an exploded view of some of the parts to get a better idea of what they look like. This is the casing. It extends from here to here. Next is the inertia mass, which attaches to the shaft. A spring-like bracket fits inside the inertia mass. The torque transfer drum is here. It's actually part of the shaft, and the drum, we said, had an opening in it. This opening allows the spring here to extend beyond the drum and to engage the bracket in the inertia mass. The spring rides here on part of the snubber casing. And finally, here's the telescoping cylinder, whose threads mesh with those of the shaft. Again, the parts fit together as shown in this cross-sectional view. Now, let's take the case of piping that is expanding as it's heating up. As the pipe moves, the telescoping cylinder also moves. This causes the threaded shaft to rotate. The torque transfer drum will also rotate because it's part of the shaft. The drum engages the spring, which in turn engages the heavy inertia mass. As long as the pipe movement is slow, which it is during normal startup, the parts will rotate slowly. The telescoping cylinder will gradually move in and the snubber will compress. The controlled movement of the pipe is not restricted. But if pipe movement is greatly increased due to sudden shock, the inertia mass will resist the movement. If you've ever tried to move a heavy object like a refrigerator, you've seen this same effect. If you apply slow, steady pressure, the refrigerator will move. But if you take a running start and come charging into it, the refrigerator will hardly move at all. You'll probably move farther than it will. In a mechanical snubber, the inertia mass acts a lot like that refrigerator. If there's a sudden shock to the pipe, the torque transfer drum will slam into the spring, and the spring will slam into the inertia mass. The inertia mass, being quite heavy, will resist being moved, and the spring will tighten up on the casing here. The resulting friction will slow the movement of the torque transfer drum. In this way, the movement of the telescoping cylinder will be slowed down, and any uncontrolled movement of the pipe will be greatly restricted. Now, fortunately, mechanical snubbers don't usually require a lot of maintenance. But if they are exposed to heavy loads and constant vibration, one of the ears on the spring will sometimes break. So, if you're ever having trouble finding out why a mechanical snubber isn't working right, remember, check the spring. Now, when you check a hydraulic snubber, make sure the reservoir has enough fluid in it. If it requires filling, consult the manufacturer's instruction manual for the proper grade and type. And remember, if the reservoir needs filling, there's a good chance that the snubber is leaking somewhere. Check the area where the piston rod penetrates the casing. The seals there are a likely culprit. Checking either a mechanical or a hydraulic snubber for proper operation can be quite an involved job. If you ever have to do it, you'll usually find yourself working with other mechanics and using special equipment. But if you know how the snubber works and you read the instruction manual carefully, you'll be in good shape. All right, why don't you turn off the tape now? And when we come back, we'll discuss 3 more piping auxiliaries: expansion joints, surge dampeners, and impact flanges. Pipes that operate under a wide range of loading conditions are going to expand and contract. There is no way around it. And unless there's some way for the pipe to give a little as it heats up and cools down, that pipe is going to weaken and eventually break. Now, in the last two segments, we looked at various ways of supporting pipes externally. We saw support structures as simple as saddle clamps and as complex as hydraulic and mechanical snubbers. Each of these components was attached to a pipe at one end and to some external support like a floor or a wall or an I-beam at the other end. Now, in this segment, we'll look at several components that are in line with the pipe. They're attached to the pipe at both ends, but allow the pipe to give a little as it heats up and cools down. Now, two of the most common of these components are expansion joints and expansion loops. Expansion joints allow for limited pipe movement up and down, side to side, and back and forth. They also reduce vibration. Generally, an expansion joint will either be one piece that flexes or two pieces, one of which slides inside the other. Now, this is a one-piece flexible expansion joint. The two pipe sections that it joins are here and here. The main part of the expansion joint is this rubber sleeve. It's often reinforced with cloth and wire to add strength. The whole assembly may be protected by a thin metal covering. The bulge here in the center is where expansion and contraction take place. If expansion joints like this fail, it's usually due to deterioration of the rubber. So when you inspect them, be sure to look for cracking or crazing of the rubber. A second type of expansion joint has two pieces or sleeves. One of the sleeves slides inside the other, allowing the pipe sections here to expand and contract. The sliding sleeve is kept from coming out of the stationary sleeve by this limit stop. Also, there's packing between the inner and outer sleeve to keep the fluid that's moving through the pipe from leaking out past the sleeves. New packing can be inserted through this packing plug. Finally, there's a lubrication fitting here. Several times a year, grease should be injected into the packing gland to make sure the sliding sleeve will be able to move easily. You should also check the sleeve occasionally for pitting and corrosion. Now, the other approach to letting a pipe give a little is to use an expansion loop. In this arrangement, the pipe itself is made into a long loop. As the pipe expands and contracts, the loop moves back and forth, compensating for the movement of the pipe. Now, during your periodic inspection of pipe hangers and supports, you should pay special attention to expansion loops. Since these loops may move more than other piping runs, their hangers and supports will receive more stress. Now, there's one more class of piping auxiliary that I think we should look at. Components that compensate for pressure changes in fluid systems. Whenever the smooth flow of fluid through a pipe is interrupted, the piping system will be jarred. When a fluid system is started up or shut down, or when water hammer occurs, the piping will take a beating unless it's protected. And two devices that offer protection against pressure shocks are the pneumatic surge dampener and the water hammer impact flange. A pneumatic surge dampener, or surge chamber, as it's sometimes called, is simply a metal tank with a rubber bag in it. The entire dampener is installed in line with the piping, as you see here. The rubber bag inside the dampener is usually filled with nitrogen gas. As the pressure of the fluid inside the pipe changes, the rubber bladder expands and contracts. The bag acts like a shock absorber to smooth out pressure fluctuations in the fluid. Water hammer impact flanges take care of a different kind of shock, one that occurs in steam lines. These flanges are designed to absorb the impact of a slug of water that would otherwise slam against the wall of a pipe. They're commonly found where there is a bend in the pipe. In this diagram, steam travels in this direction. If a slug of water were entrained in the steam, it could end up slamming into the wall of the pipe. This is called water hammer, and it can cause very serious damage to piping systems. One way to protect against water hammer is to extend a section of the pipe just downstream of a bend and install a water impact flange, like you see here. The flange consists of an orifice plate, a metal cone, and a second metal plate, all welded together. When steam and entrained water reach a bend in the pipe, the steam makes the turn easily, but the water, being denser and heavier than the steam, can't make the turn. It keeps going straight, hitting the orifice plate. The plate absorbs part of the impact, but some of the water passes through the hole in the orifice plate, hitting the metal cone and the second plate. Usually, they can absorb the rest of the impact. Sometimes, though, the impact will be so great that the cone and plate will break right off. Now, if this happens, the flange assembly must be removed and rewelded. Well, we've now seen several of the most common types of piping auxiliaries. We looked at strainers and filters and saw how they remove contaminants from fluid and air systems. We examined some of the ways that pipes are held in place. We looked at ways to allow for expansion and contraction in pipes. And finally, we looked at ways to absorb shocks to a pipe and within a pipe. There are even more piping components that you'll learn about in other units. Components like vacuum breakers and moisture separators. And even though some of this equipment may require only occasional maintenance, it's all vital to the operation of your plant. The day will come when one of these reliable components fails. And when that happens, a lot of people will be standing around waiting for you to fix it. So the more you know about how these components work and what their job is, the easier your job will be and the happier you'll be. All right. You can turn off the tape now and review the material that we've discussed.